Hey everyone, I haven't recorded a video in a while. I've just got my sound system all set up here. I think I'm going to have better sound in my home office here, so I hope it does sound better. Well, anyway, let's go ahead and get started. I'm Michael Pyrcz. I'm a professor at the University of Texas at Austin, and I'm teaching a course on machine learning. And we've already covered a bunch of the fundamental concepts. The last lecture got into prerequisites for machine learning, the concepts behind it. Before that, the lectures were all getting into concepts of probability, feature engineering, data preparation, and feature selection. So let's go ahead and talk about our first type of machine learning. Now what you'll notice is that we are, in fact, for the rest of the course, just going to have every single lecture is going to be a different type. We're going to go through a big toolkit of machine learning methods, and we want to start with some inferential methods to start it here. And so our first inferential method is going to be clustering. Now, why did I pick clustering? It's pretty straightforward, but it's also very powerful technology. It's really widely used, and it can be quite helpful to you. So let's go ahead and motivate and talk about what we mean by clustering. So what we want to do is we want to detect patterns, sample clustering, training data samples that are clustering in the predictor feature space. So every time I talk about predictor features, we're talking about x1 through xm, where m would be the total number of features that we've selected for our predictors. Now you notice we're working with unlabeled data. In other words, there's no y's. It's inferential. We're trying to understand the system. We're not worried about building necessarily a predictive model to make predictions of y's. So no y's, we'll just have our features. Now it's quite a simple and visual method to work with, because what happens is that, well, let's take a look here. We've got acoustic impedance on the y-axis. We've got porosity on the x-axis. And maybe we're interested in grouping up our rock in the subsurface in a way that's natural and intuitive from the standpoint that it covers not only the petrophysical aspects of the rock, the things you would measure in the wells and with the cores and so forth, but also the acoustic impedance, the geophysical aspect, the things we'd be recording more directly with seismic. Now, of course, we can measure both in both, but at the same time, in general, we have geophysical measures and petrophysical measures. We might want to break up the rock so that it's different in both. And that would be very useful for making predictions with seismic or well data in different locations in the reservoir. So we want to break it up. We want to form different groups and see natural clustering. And so we gave ourselves a data set here, which has an interesting pattern. We'll be working with it during the entire lecture, so we'll get back to it right away. We're going to teach concepts like feature transforms and distance metrics in the feature space. So this is pretty useful stuff. Let's first just mention what prototype methods are. We'll explain a prototype very quickly, one slide, and then we'll go on and get into clustering. Now, what is the idea of a prototype? We want to represent the training data with a set of points in the feature space. Each one of those points is a prototype. Now, what's interesting with most methodologies, the prototypes are not typically an actual sample. They're not. They're representative of the samples, but they're not an actual sample in the sample set. Training data are often assigned to belong or to be owned by the nearest prototype using some measure of Euclidean distance in the feature space. Now, we'll go ahead and talk about this kind of approach of nearest neighbor assignment and so forth right away here. But for now, let's just understand that we have a feature space. And when I say feature space, I'm talking about the range of each one of the features, permeability, porosity, and that entire space included there. Now in this two-dimensional problem, the feature space is just a two-dimensional map of the range of each feature across in each axis. Now, if we had three-dimensional, four-dimensional, five-dimensional, in other words, we had 5 features to work with, of course this would be a more complicated space, but we could project and look at it in 2D from different directions, or we could try to visualize it in 3D with projection to 3D and so forth. But we have our sample data. Our sample data are available. We can plot them. If we have values available for us in each one of the features, we can plot it and look at this feature space. And then what we would have, these prototypes would be deemed to be representative of these groups in the feature space, but the prototypes are just going to be a specific value for each prototype, a specific value of each one of the features. Porosity equal to this, permeability equal to that. That's the yellow prototype on the plot. The red prototype would be porosity that's lower down here, permeability here, and that would be its prototype. But you notice that's not one of the sample data. In fact, it's just representative of the subset of the sample data. And so we can use prototypes. Why do we bring that up? Because the methodology we'll talk about today, K-means clustering, is in fact a form of a prototype method. So we want to be prepared for that concept. So let's make a couple more comments around clustering just in general. One of the most important, powerful inference methods, you'll run into it all the time as you're doing machine learning. It's a great way to learn about our data, to find the natural groupings within potentially high-dimensional data sets is pretty useful. Known as clustering, cluster analysis, automatic classification, numerical taxonomy, so many different names for it, but it's all really the same thing. It's partitional is one method we can use where all the clusters are determined at once. K-means clustering, which we'll focus on today, is partitional. More flexible, because what happens with this methodology is that there's an iteration to the solution. So it has flexibility to be able to, it does not lock into the data, it can be adaptive. Hierarchical approaches are different. They go stepwise across different scales. And so they lock in as they go, and they may be a little bit less flexible. But being hierarchical is a very powerful thing. You imagine many natural phenomena behave differently at different scales, so it can be very powerful to use a hierarchical approach. The agglomerative approach is a bottom-up type of approach where you start with every one of the training data samples within their own category, just hanging out there all by themselves. They're each in their own cluster, and then you'll merge them in a natural way using usually some form of heuristic rules. Merge and you'll build up groups of fewer groups but larger size in the groups. Divisive is top-down. You'll start with all of the training data samples in one big group, and you'll use rules to divide up the group, and you'll usually stop based on some stopping criteria. Now, it's a little bit less flexible than the partitional approach with the hierarchical, because once you merge or split, you can't undo it. So you could imagine locking into some features that might be suboptimal as you try to move across different scales. So what's the goal of clustering? What are we actually trying to do? We're trying to assign clusters or groups to all of the training data in the feature space, such that the groups are exhaustive. All of the data belong to one of those clusters. In other words, the probability union of all clusters is going to be equal to 100% in general. Now, there are some other types of methods aside from K-means clustering that will accept outliers. In other words, some data are left unassigned, but this is the case for any K-means clustering type of approach. The groups are mutually exclusive. That is the probability of being a member of more than one cluster, the intersection of any cluster for which the index for the clusters are not equal to each other is equal to 0. Exhaustive, mutually exclusive, categories assigned to the data. Now, mathematically speaking, what are we actually trying to do? We're trying to assign those groups to minimize the difference between the training data in each group. In fact, we can write it out like this. W is known as inertia. And if you look at this equation, it's not too complicated. This right here is a squared difference calculation. Now note xi and xj are just simply two training samples within our data set, and we've constrained it such that they cannot be equal to each other. Therefore, we're never comparing data with themselves. So this calculation right here, this x would be a vector over all of the features. So the value for the training data for all the features. This is another vector for all of the training values for the features. And so this difference squared is a distance between the two samples in the feature space. It's like calculating Euclidean distance, but in feature space, not in the regular Euclidean space that we work in with the world around us. Now, if we look at the double sum is just so we can compare all of the possible training data with each other. But what we're going to do is we're not going to compare all training data with each other. We're going to constrain ourselves to work with only the samples in the clusters. And so this right here is simply saying 1 over the number of data within each cluster, compare all of the data within a cluster to each other, and get an average of the distance. Then we're going to get the sum of those average distances within clusters over the clusters. K equals 1 through K number of clusters that we're working with. Quite straightforward. So what are we going to do? Well, W is our inertia term, and we're going to try to go ahead and minimize that. We want to minimize the distance between all the samples within each one of the clusters. So that's the mathematics behind it. We could try to draw it. Now, if I was to actually draw it perfectly, exhaustively, it would be very noisy. So all I've done is drawn these vectors to represent the distances between these pairs of samples within group 1 and within group 2. Now, I've done this incorrectly. I have not been complete or comprehensive in doing that, because you notice we'd have to draw a vector between this sample and this sample, this sample, this sample, between all the other samples. You see that? Because we would be comparing the distance between each of the samples, training data, and all of the other samples in the cluster. That would be a mess, so I didn't do that. I hope this helps. But by trying to minimize that, we're trying to formulate groups that have the least amount of difference within the group. That's pretty cool. That's going to be a good thing to do so we can identify clusters or data with similarity to each other. And so that's what we're trying to get done here. Now, some general comments on K-means clustering. It is a large solution space if you imagine. There is so many different combinations. In fact, you could calculate the combinatorial of, for a set number of groups, K groups, how you can divide the data up. But even though it's a very large solution space, it turns out it can be practically solved iteratively. And so we'll show that, and we'll actually step through it with code in Python on the slides, and I have a demonstration and a workflow on GitHub, so you'll be able to see it all. Now, one problem is that the solution surface to this problem is not going to be nice and smooth and well behaved. It's not going. So when we use a iterative approach and we're trying to search for the solution, there is a good chance that we'll be stuck in a local minima. That happens all the time. The practical solution within cluster analysis is to seed multiple starts, random starts, so that when you get stuck in a local minima, well, if you do enough random starts, you hope that you've explored the space well enough to actually find a global minimum or a really good minimum to work with. So we do multiple starts, converge on each one of them, and take the best solution by looking at that previous equation of the sum of the average difference within each one of the groups, the inertia term, the W. I'm just going to refer back to our previous discussion on the cursor dimensionality. All of the issues that we brought up before with regard to understanding our data and working in very high dimensional spaces still stand here. In fact, there are some other issues that may creep in. First of all, distances may become very similar in a very high dimensional space, and so it may become more difficult to be able to discern the robust set of clusters if we inflate or work in a very large dimensional space. Data coverage may also be very low, and so it may be very difficult to discern this is a cluster, in fact, or this is a cluster. They may not have the nice kind of groupings that may be very helpful for us to be able to understand. So, cursor dimensionality, hard to figure out the clusters if we don't have a lot of data to be able to understand and explore a feature space, the high dimensionality. Same problems we talked about as far as cursor dimensionality in previous discussions. Some comments further on K-means clustering. Clustering of training data in a feature space to identify similar cases, similar examples, distinct subsets in a multivariate data space. That's super cool. That's very useful to figure that out. Unsupervised learning, the data is not labeled, and they're going to be assigned. We'll come up with them with the clustering method. It's inference. We're working really with all inputs. We're not trying to build a predictive model. It's a prototype method. Represents the training data with a number of synthetic cases in the feature space, not actual sample cases, but we'll make prototypes representative of each group. For K-means clustering, we assign prototypes. It's an iterative solution. As I mentioned before, initial prototypes are assigned randomly in the feature space. Labels are assigned to all of the nearest training data, and then we update the prototype. Repeat, repeat, repeat until we converge, until we stop changing the prototype locations. Now, I've said that in words. I'm going to show it to you in steps, and you're going to get a chance to see it, so don't worry. Now, just a couple of comments. Feature weighting. The procedure depends on a measure of distance. I showed it to you already. We're calculating the square difference between all of the sample data, the training data, using the vectors that represent the various measures, or all of the predictor feature measures. Now, if the features have significantly different magnitudes, the feature with the largest range, or I should say the feature with the largest magnitude, will dominate the process. You can imagine if I have one feature that ranges between 0 and 1 and another feature that ranges between 0 to 1,000,000, any offset in the feature that ranges from 0 to 1 will be swamped by the other feature in the distance calculation. It won't even matter. And so I'll show you an example. I'll show you what happens. So what we're going to do is we're going to apply a standardization. Now, fortunately, we just covered standardization among over a bunch of other feature transformations in the previous lecture. Okay. Also, bi-feature weighting may also be applied. You may want to put a bias within this model, and so you could. You could put a weighting in the distance calculation to favor one of the features over another for the decision of the clusters. There is a supervised learning classification variance. So if people hear this and they say, well, Pyrcz said it's unsupervised. Well, no, there's a classification methodology that is, in fact, cluster-based. And I'll have one slide at the very end where I'll just show you what that is. Okay, let's start with our data set. This is exactly the same data set we had before, acoustic impedance and porosity. It's a nice data set. It's pretty well behaved. We've got enough samples we can start to see something. We want to segment by petrophysical property and a geophysical property. So we have maybe a rock type that not only accounts for flow behavior, porosity, and also accounts for imaging, the ability to image it. So that would be very powerful. That'd be a good thing to do. So what are we going to do? We're going to have to segment this up so we have multiple groups or rock types that we can work with. Now we're going to have to consider a measure of similarity. Now our example is pretty straightforward. We're going to use our regular equation we would use for Euclidean distance if we had x and y and we're working in 2 dimensions. We would just calculate delta x squared plus delta y squared, take the square root of that, and that would give us the distance between the two locations. But instead of having x and y, we have features. We're in feature space. So we'll have the difference in the porosity squared plus the difference in acoustic impedance squared. Now, for dissimilar units, we're going to require a form of standardization normalization. Otherwise, we're going to have an issue. Why? Let's look at this data set right here. Acoustic impedance, it's going between 2,000 and 6,000 right here. Porosity, 0.12 to 0.28. What's going to happen is any samples that have any offset in the vertical direction are going to look like a big difference or big distance. And any samples that have an offset in the horizontal location are still going to seem very close to each other. And that's going to affect the geometry of our clusters that we're going to form. So we want to remove that. We're going to go ahead and standardize. Now, we go ahead and we standardize our data set. And if you look at it right now, we've done not standardization. Let's just do normalization. So we're forcing the minimum to be 0, the maximum value to be 1, from 0 to 1 on both of our features. Now, in all directions, we have the same distance. If you've gone the same offset and you scan around, it's going to be the same distance. And so that's a pretty nice way to work. Now, once again, we could have employed some type of weighting. We could have said acoustic impedance difference is more important than porosity difference, or vice versa. Okay, so we've done our normalization. The first step of clustering with K-means is to assign K prototypes. Now, we have to make a choice. How many prototypes, how many clusters do we want to try to form? That's a requirement with this method. Now, the methodology is going to have multiple random starts, and for each random start, it's going to go ahead and assign a random prototypes. Now, I want to make a point right now. the prototypes can in fact be very, very bad. They're not very good. Like, look at this. This would be a terrible prototype. It's not representative of any of the samples. This one's not great either. This one's not good. They could be outside of the training data. That's fine. It should still be able to do a pretty good job. And we'll do random starts so if we get stuck in a local minimum. Now, what we'll do from now on is so people can visualize and understand what's going on, I'll display the data in the original feature space, original units of acoustic impedance and porosity, and in the normalized space, porosity and acoustic impedance. And so here we go. We got our prototypes, blue, red, and green. 3 of them, blue, red, and green. You can see that. Okay. Now what we're going to do is we're going to assign all of the training data to the nearest prototype using our measure of distance that we discussed before. This is iteration number 1 of our clusters. How's it look? Not very good at all. We haven't done a really good job of breaking it up. In fact, if I was to calculate the sum of the average distance between all of the samples in each one of these clusters, it'd probably be a really bad result. And so we know we're not doing a great job. They're not very good. Well, let's keep iterating. So what we do next is all we have to do is we take the prototypes and we're going to offset them to the centroid, in other words, the average in the x and the y, of each one of the sets of training data assigned to each one of those clusters. So if we do that, we're going to move like this. Our prototype went here. Our blue prototype went in the middle here. The green prototype went in the middle of the green examples right there. Now, if you think about it, now we have a problem. The actual data, training data, are not any longer assigned to their closest prototype. So let's go ahead and fix that. We've improved the prototypes, now improve the assignment of the training data to the prototypes. So let's go ahead and do that. We just did that, so I can toggle back and forth. Do you see the change? Pretty cool, right? You can see how a lot of these were red, and now they became blue. You can see some of these were green, and now they became red. So it's like a war going on between the training data, and now we've established that, okay, this is a better set of training data for each prototype. But we have a problem now, right? The prototype is no longer in the centroid, therefore really nice and representative for each one of these clusters, so we've got to move the prototypes. Do you see that? Well, we could keep doing this over and over again. I've shown like 2 iterations. If you iterate over and over again, this is eventually what you will get for the clusters. Prototype, 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 cluster green, cluster blue, and cluster red, regular space, normalized space. This is really interesting. This method works very well to minimize the sum of the average distances between all of the training data within each one of the clusters. Now, as I mentioned, we could have done multiple random starts, and I could have shown that within the scikit-learn that will demonstrate the scikit-learn method for clustering. You just have a parameter where you can set the number of starts, and you set it just large enough and it's able to explore. The algorithm is pretty quick. Now, of course, it's going to be sensitive to the number of clusters that you assume that you're going to be working with. You have to make that choice a priori, the number of clusters you want to use. And so you can see right here that if you use 2, regular space, normalized space, 7, regular space here, normalized space here, and you can see in general the grouping or clusters that we form. They seem very logical. They seem to honor this idea of minimizing the distance within each one of the clusters. Now, just a comment I'll make again on solution uniqueness. There exists a unique solution that will minimize the inertia. And yet the response surface is not very smooth, as I mentioned before, quite likely trapped in local minima, so we're going to do multiple starts to try to address that. Now, that's about all I can say about K-means clustering. It's pretty straightforward to work with them, very powerful, but there's a whole variety of assumptions that we make with K-means clustering. And so in general, we're going to assume that the clusters are spherical. Now, that would be hypersphere if we're working in greater than 3 dimensions or 3 predictor features. But in general, spherical, convex, isotropic clustering that's not aligned in one specific direction. then we'll minimize the distant difference within each one of the clusters. Now, we're also assuming, now what would be the problem? Well, come over here and let's look at this data set. Now notice this was taken directly from this site here, this image right here. Thank you very much. But we can go ahead and look at this example here. If I looked at this just ocular inspection, I'd probably want to break it up with maybe this as one cluster and this as another cluster. K-means clustering does not work like that. It's looking for spherical clusters. It has no way to understand the shape. This fundamentally nonlinear type of behavior and very kind of complicated, really a complicated type of pattern. So it would fail. K-means clustering, two clusters would do something like this. It's also assuming equal variance for all of the features. Now I mentioned before we're going to do some type of standardization. We're going to do some type of normalization standardization. Now, one caveat here or exception would be, what if you have two features and they're fundamentally measuring the same physical phenomenon? In which case, the difference in magnitude or variance is meaningful. It's not arbitrary. In that case, you may want to in fact keep normal units so you can account for that or use some type of weighting after the normalization. Now, another interesting point is that there's an assumption with the methodology that there's an equal prior probability for all of the clusters. All of the data start out with equal probability belonging to each one of the clusters. We're not working with any type of prior that any of the data are more likely to belong to other clusters. We're working with a naive uniform distribution. Another comment is that we're assuming there's similar size or frequency, number of samples in each cluster. Now let's take a case right here. We have an example where we have a cluster with a whole bunch of more data, and I want to credit this website, which I took it from. Thank you very much. The link is shown right here. But clearly there's a cluster here, a cluster here, and a cluster here, and they're all spherical. But when we go ahead the calculation, we end up breaking this up because of the fact that there's so many samples. It's effectively swamping these samples right here. Okay, so those are the caveats. These are some of the issues with the methodology. Now, there are variants of clustering. Of course, there's many types of clustering, and I've only talked about K-means clustering. But there is another methodology. It's known as the Kmeans clustering. It's a partitional method. It's not hierarchical. When you use the actual training samples instead of prototypes, we're going to swap randomly if a cost function is reduced. The cost function right here is simply going to be the summation of the difference between the individual samples within each one of the clusters and the value of that medoid, the value that's representative of the cluster. If there are k medoids in a training sample, there'll be with non-medoid samples x1 belonging to each of the groups. And so it's less sensitive to outliers than K-means clustering. Other limitations of K-means clustering remain though. Another form of clustering is DBScan, which is density-based spatial clustering of applications with noise. It is a hierarchical method and it's bottom-up. We're going to try to actually grow our clusters from the training samples in the predictor feature space. Now, it's a density-based clustering methodology. So this is kind of fascinating. It's going to try to identify cluster locations based on locations with enough data, high enough density of training data available to form a cluster. And then it's going to try to grow that to adjacent locations based on where you have sufficient number of data or clusters. And if we have data that are isolated with each other and cannot be connected to these growing clusters, we're going to give up. We're going to declare they are outliers. And remember what I said before about K-means clustering being exhaustive? This methodology is not. It's willing to accept some of the data just don't fit in. So this method is quite sensitive to the parameters. What are the parameters? The maximum radius of the neighborhood. When I'm trying to find enough points to start a cluster, how far am I willing to look around a training data value to identify enough points to declare this as a cluster, and the minimum number of points to form a cluster. Those are very, very important, and you could see if you the results if you do a poor job of selecting those parameters. So what's the workflow? We're going to visit the training data at random. We're going to check around the data using that neighborhood. If there's enough points, we'll declare, that's a cluster. We're going to start a cluster, and we can add that data value to a cluster. Or we might identify that it's within the neighborhood of another cluster, and we can decide to add it to that other cluster. We're growing that other cluster. If there's not enough points around and you're not beside another cluster, you could assign it as an outlier. And you just go like that. You randomly go to different locations. What'll happen is you will grow your clusters, and they can be unequal in the density or number of samples in each one of the clusters. That's not a problem. Non-spherical? No, they can have all kinds of complicated shapes. That's okay too. And what's interesting, it identifies outliers. This is, in a way, you could see it as being more robust in the presence of outliers, where a K-means approach would be more sensitive. That would have an impact on the overall quality of the cluster. Now, if you go online and you look at scikit-learn, you'll find in their documentation on clustering this wonderful figure right here, where they've got 1, 2, 3, 4, 5, 6 different data sets. You start out with them, and then you apply each one of these different clustering methodologies to them, and you can look at them and see the general behavior of the clustering methods. We have just scratched the surface in clustering. We've only explained K-means clustering really thoroughly. The other two methods, honestly, we've kind of just given you a taste of what they're all about, but really not shown any examples or really helped you with it. There's much more we could do on clustering, but for the purpose of this lecture, we're going to stop right here with regard to showing clustering methods. There's a hands-on exercise that I'll record in a separate video, and I will walk through this with my students in class. This is, I think, a well-documented exercise in scikit-learn doing clustering, and it actually does it by hand. It's the example that I showed on the slides, and so you can walk through and see how you do that with code with some nice little subroutines or functions. Now, I mentioned I was going to explain the idea of K-means clustering for classification, or what that looks like. Not a big deal. What you do is you in fact are working with labeled data now. Okay, so you have labeled training data. This is prediction. This is classification. The facies labels could be included below. We got permeability, porosity. We got a bunch of red facies, red category. We've got a bunch of yellow facies. Now, what are we trying to do with classification is we want to segment this feature space so we can say this is the red category, this is the yellow category. What are we going to do? We're going to apply K-means clustering in each one of the categories. So you got to make a choice. How many K-means are you going to use within each one of the categories? Now, what's interesting, that's a hyperparameter, because if you use many prototypes or K-means, Ks, in each of the categories, you'll get a very complicated decision boundary. If you use only one, you would actually get a simple linear. It would be the perpendicular bisector between the two prototypes if we just use one prototype for each one of these categories. But let's go ahead and pick 3. For the red category, we would have 1, 2, 3 prototypes. For the yellow category, 1, 2, 3 prototypes. All we have to do is perform K-means clustering within each one of the previous labels that we have assigned to this training data set, red and yellow. And what that'll do is it'll put the prototypes in really good locations as far as representing the space or the spatial form of each one of these facies that we want to try to model. Once we've done that, now what we can do is we can build a decision boundary that is based on the nearest prototype from any one of the categories. Now you could imagine if we use 100 prototypes, we could get a very complicated decision boundary. And if we use only one prototype within each one of the facies for 2 facies, the decision boundary would literally be a linear decision boundary, the perpendicular bisector between each one of those prototypes. All right, I hope this was helpful to you. Like any of the machine learning lectures that we'll have from here on in, we'll cover the fundamental theories, some of the concepts, we'll demonstrate some of the more simple methodologies, and at times we may not be able to cover the wide range of different methods. Machine learning is vast. There's so many methodologies that are available, of course. I hope this was helpful to you. I'm Michael Pyrcz. I'm an associate professor at the University of Texas at Austin. I am also the Geostats Guy on Twitter. My lectures on YouTube are under the channel Geostats Guy Lectures. I'm always happy to discuss. I record these videos and put them online for anybody. Every one of my lectures at the university are available to anyone in the public, anywhere who's interested, because I'm all about outreach. I hope it helps people, and I'm excited to get good feedback. If you're using this material and it's helping you, if you're a working professional trying to address digitalization, go ahead, fire me an email. Let me know if this is helpful to you, and I'm open to suggestions. I'm all about trying to help people with the digital transformation. All right. Thank you very much. Take care.